have Igor Oliveira speaking about probabilistic complexity.
Okay, thanks everyone for staying. So my plan is to give an informal introduction to probabilistic notions of Kolmogorov complexity. And the main focus of the presentation is going to be on the definitions, or even like in the ideas behind the definitions. But along the way, I'm also going to mention some results and directions. And because this talk's being recorded, I'm going to briefly review some definitions. So there's some overlap with what you have already seen, but shouldn't be too much. Okay, so Kolmogorov complexity. So informally, we can think of Kolmogorov complexity of a string as the length of its shortest encoding, and introduce k of x as the minimum length of a program m that outputs x. So this is only an informal way of thinking about Kolmogorov complexity. So more formally, so we fix Turing machine U, and we define the Kolmogorov complexity of a string x with respect to U as the minimum length of a string m such that U of m outputs x. And as Eric was explaining, there is a robustness in this definition. So if we pick, we are careful about picking the machine U, then this definition won't change much. So in the time-bounded setting, it's often convenient to take what is called a time-optimal universal machine. So let me just mention this. So it's possible to pick a machine U such that for every machine M, for every input X, and for every T, we have, for this special universal machine U, that its Kolmogorov complexity with respect to U is going to be at most KMX plus some constant C that depends on M. And there is a small overhead in the running time, so it goes from T to roughly T log T. And we also have a constant here. But it's possible there's a machine like that, and that's how you usually like you formally define the time-bounded Kolmogorov complexity. So this definition for now only talks about Kolmogorov complexity without running time. But once we fix this U, it's going to be a time-optimal machine for us because we'll be mostly interested in time-bounded Kolmogorov complexity. Okay, so that's the about the formal definition. However, for simplicity, so for this talk, I'm going to abuse notation. I'm going to refer to these machines directly and talk about these encodings. Okay, so when I designed these slides, I wasn't hoping that Eric would be in the audience. So I'm just hoping that he won't leave the room right now. But so yeah, and everything I'm explaining today is covered in a formal way at this survey, which I wrote together with Tenji and Lu last year. So theory and applications of probabilistic Kolmogorov complexity. And there we also discuss in detail why you shouldn't use this definition. Okay, thanks to Eric. But for this talk, we're going to follow this convention just to simplify the presentation. Okay. Okay, so time-bounded Kolmogorov complexity. Here's the definition of the unbounded case. There are different notions, as we have seen. And one important one is called K little t. It's the Levin Kolmogorov complexity. And here we minimize not just the length of the representation, but also we add a log of the running time to the measure. Okay, so kt of a string x is the minimum over encodings plus log t, such that this machine outputs x within t steps. And there's another notion of time-bounded Kolmogorov complexity, which is useful when, say, you want to talk only about polynomial time machines, and that is the k superscript t complexity for a fixed function t. Now here we don't need to add the log t, but we focus on machines that will run for at most t length of x steps. Okay, so there are these two notions, k subscript t and k superscript t. And time-bounded Kolmogorov complexity is something that has been studied for decades in complexity theory. So for instance, there's a really nice paper of Sipser where from the 80s, where he uses time-bounded Kolmogorov complexity to give a proof that BPP is in the second level of the polynomial hierarchy. I highly recommend you to have a look at that paper. But over the last few years, it seems that these applications and these connections between time-bounded Kolmogorov complexity and other areas, they have exploded. And I just want to highlight here 3 recent results. We're going to see more about them probably tomorrow. So the first is this characterization of one-way functions obtained by Liu and Pass, where they showed that one-way functions exist if and only if computing k superscript t for polynomial t is mildly hard on average. Okay, so we can completely characterize the existence of cryptography using the hardness of a meta computational problem. Soichi has also found this really nice result connecting worst case and average case complexity. And the statement says nothing about Kolmogorov complexity, but the only proof we are aware of uses it in a crucial way. So we also have applications in average case complexity. And finally, a result that wasn't mentioned yet, but was also recent and very interesting, is a characterization of the randomization of BPP using hardness of another Kolmogorov complexity problem. So we can use time-bounded Kolmogorov complexity in several areas, and we have like already quite exciting examples, both in crypto, average case complexity, and the randomization. Yeah, let's wait for the presentation tomorrow to get this presentation. Okay, so it's obviously very important to understand these notions. But despite all these recent applications, there are still very basic questions that we don't know how to address about these time-bounded notions. So for instance, if we believe cryptography exists, then it should be very hard to compute Levin's complexity, say to show that this is not in P. It's one of these long-standing questions. We don't know how to solve that yet. Eric was also telling us about these key results in Kolmogorov complexity, symmetry of information, coding theorems, and it will be extremely interesting to understand whether they still hold in the time-bounded setting, given the number of applications we have for them. Also open. And finally, Kolmogorov complexity is also deeply connected to explicit constructions, where if you have an explicit construction of an object, then you have a way of encoding it succinctly by the code of this algorithm that generates the object. And it makes sense to ask for natural mathematical objects like prime numbers, do they exist and at the same time with short complexity, right? That they have short encodings. This is also connected to long-standing mathematical questions. So we would love to understand these questions and these time-bounded notions better, but it's been very hard. Hopefully in this program, we're going to be able to make progress. So what I want to talk about today is how a more recent theory of probabilistic Kolmogorov complexity can give us some new insights about this classical question. So here's an overview for the talk. I want to introduce these probabilistic notions and at the same time mention one recent advance related to them. Discuss how they relate to the classical notions, the deterministic ones, and then discuss 2 applications of a recently introduced notion called PKT in the context of average case complexity. But as I said, the focus of the talk will be really in the definitions and how they were discovered. And so I'm going to be focusing on like why to define things in certain ways and, given the context, how we're going to use them. So that's going to be the main focus. Okay, so let's start off with probabilistic notions. And by the way, do stop me if you have any questions. Okay, so here the idea is how do we port time-bounded Kolmogorov complexity to the realm of probabilistic algorithms? Because this is the algorithms we use everywhere, like in cryptography and so on. So it's the motivation is there. We would like this theory to be useful also in the context of randomized computations. But at the same time, we know randomness produces strings of very high Kolmogorov complexity. So we have to be careful. So the definitions, they are inspired by the notion of pseudo-deterministic algorithm. So recall that this is a randomized algorithm that produces the same input with high probability. So we have a randomized procedure. If you look at its code, it's a deterministic object. So you still have a deterministic encoding. But the way you decompress your string from this deterministic encoding is a probabilistic computation. And what we hope is that it generates the same canonical output with high probability. So we really focusing here on the decompression aspect of the theory. And so let's first look at Levin's complexity. So this is just the original definition in the deterministic case, where we minimize the length plus log t. And the way to introduce randomness to this definition is very natural. So now instead of minimizing over deterministic machines, we're gonna minimize over randomized machines. So you have a Turing machine with a random tape, that's the machine M. And now we say, given a string X, this RKT complexity is gonna be the minimum over the length plus log t, such that the machine M outputs X in at most t steps with probability at least 2/3. Okay, so you have this representation. It's likely to generate X. It might fail with small probability. And if the RKT complexity is bound there, you also know it won't run for too long. Questions about this definition?
So is this definition robust for amplification, right?
Yeah, that's a good question. Yes, you can. It's a robust definition. So if you want to make this 1 minus delta, or even if you want to go from delta to 1 minus delta, you can do with some small overhead.
It doesn't matter if the machine performs. Will they halt at t-steps for sure, or?
Yeah, so you could consider two definitions.
You know what I mean?
Yeah, you could, like you're talking about, like when it doesn't stop and it produces X in t steps. Yeah, the way I define here, it could run like forever, but this won't change the definition by more than like a log n additive factor. Essentially, if you're talking about running times up to the n, you could just store this exponent n with log n bits, and I will stop the machine. More questions about the definition? Okay, so I want to move right away to a result that currently we can show for these randomized notions, but we don't understand yet in the classical context. Okay. So here's the question: is a meta-computational problem, and it's connected to this idea of, is it hard to detect patterns? Okay, so the problem is the following: I give you an input X, and you need to decide whether it's a structured string, meaning its RKT complexity is at most into the epsilon, or whether it's a random string which has close to maximum complexity. Okay, and I don't care about what happens in between. So we're trying to distinguish between structure and randomness for this notion of Kolmogorov complexity. And we would like to show that this is a hard problem. And in particular, if cryptography is possible, we shouldn't be able to solve this. So that's one motivation to study this question too. And a few years ago, I noticed that if you look at these randomized notions, then indeed we can prove an unconditional lower bound. So this is in contrast to the deterministic case where this remains open. So more precisely, we can show that we can distinguish between these two sets of strings using a randomized machine of quasi-polynomial time complexity. Okay, so it's a super polynomial lower bound for this problem of estimating complexity, and it's unconditional. But yeah, so this makes the problem easier because now I have a smaller set of inputs, but the theorem says it remains a hard problem. Any other questions? Okay, so shortly after proving this, I was very interested in trying to make this quasi-polynomial time exponential, because you would expect that there isn't really a better way of doing it except for maybe trying out representations of complexity up to n to the epsilon. Yeah, I couldn't do it using this proof technique, which is an indirect diagonalization. But recently, Suichi has found a different approach based on symmetry of information. And he proved that indeed the problem is hard for exponential time computations. Okay, so even if you run for to the gamma n time, you can't compute exactly the RKT complexity of a string.
What the exact gamma is?
No, I don't think we have tried to optimize. Yeah, I don't know what is that.
That no problem with that thing through them.
Okay, so yeah, let me talk about this too. So here, let's say you want to compute it exactly, so there's no promise. Then you can show it's not in this class. The result admits a small additive gap, but it has an interesting caveat, which is that you must assume that the machines, the acceptance probabilities are bounded away from half, even in the non-promise region. And I think it will be very interesting to try to unify these two lower bounds, because one of them is for the approximation version of the problem, and I don't need to assume bounded probabilities. The other one goes all the way to exponential hardness, but it has this caveat. So if you're interested in trying to understand these lower bound proofs, think about maybe how to try to connect these two approaches and generalize the lower bound. And I also want to highlight, like, you might ask, why can we do it for randomized algorithms, for randomized notions of Kolmogorov complexity, and we can prove the same lower bounds for the original problem, like k little t and mktp. And the reason is it's a proof ultimately by diagonalization. So you want to use algorithms to diagonalize. And once we live to the randomized world, we know how to do more things with randomized computations. So in particular, this proof here uses random self-reducibility, which is a way of moving from like to translate between average case hardness and worst case hardness. And these are randomized procedures. So that's why we had to live to the randomized case to get the lower bound. Any other questions about this?
Sorry, could you repeat what MRKTP is?
Yeah, so these are like minimum complexity problems. And in this case here, the notion of complexity is RKT. So given a string, you want to, and given S, and you want to know if this RKT complexity of the string X is at most S.
Can you repeat what the caveat was? I missed the caveat.
Yeah, so in this statement here, there's no caveat. It's like there's no promise. But if you want to talk about approximation version of the problem, right? Like you don't care about some things, then in this proof, you need to assume that the randomized machine, its acceptance probability is bounded away from a half. Although you don't care if it's correct or not on those inputs. Something funny with the proof. Okay, so that's Levin's complexity in its randomized version. So now we can also look at the polynomial time regime of fixed time bounds. Here's the original definition without randomness. And again, it's very natural. You can consider randomized version for this notion. So you're talking about randomized machines that run for t length of x steps and output x with high probability. There's no log t because the t is fixed. It's just the analog motion. And yeah, that also mentions something we can do with this notion that we don't know how to do with the deterministic case. So it's connected to the problem of explicit construction of prime numbers. So I give you 1 to the n, and I would like to generate an n-bit prime. And this is a difficult question. Best algorithms, they run in exponential time. And by using this connection discovered by Levin that relates universal search and KT complexity, this problem is equivalent to showing that there are primes whose KT complexity is small. Okay, so we would like to show that for natural objects, they have small k little t complexity. Yeah, this is still open, but once we move to the randomized case, together with Rahul, we show that actually there are primes whose RKT complexity is subpolynomial. Okay, so we have short encodings for infinitely many primes, but for Levin's notion, the running time can be exponential. So you get this log t. And what more recently we were able to achieve together with Tinjan is not only to upper bound the RK little t complexity, but the RK poly complexity, where the running time is fixed to be a polynomial. So now we can show that there are infinitely many primes such that not only you have a succinct representation, but the running time, the decompression is also efficient. And again, it will be really interesting to get these results for the deterministic case, but we still don't see how to do it.
What are the properties of primes that you use here?
Yeah, that's a great question. So the only thing we use is that you have like a set of strings. So let's say you have some language, and you have a dense set of yes instances, and the language is easy. Say it's in P. So for the case of primes, we have an easy problem that is dense, and we have a technique that says in such a case there must be an yes instance whose complexity is bounded. So yeah, it's a much more general result, although this might be one of the most interesting applications. Okay, so for most of the talk, I'm going to talk about this more recent notion called PKT complexity, which is also a probabilistic notion. And so we submitted this paper last year. Fortunately, it was accepted. But one of the reviewers said, you know, additional results are obtained for yet another variant of Kolmogorov complexity. You know, I can't blame the reviewer because there are so many of them, right? But I want to try to convince you today that this is indeed a very interesting notion. You know,
another very interesting notion.
Like you should be excited about this new notion. Okay. All right, so yeah, stay with me. Okay, so it's a bit of a mouth, the definition, but let's first read the sentence here. So what is happening with PKT complexity? It's called it's a probabilistic t-time bounded Kolmogorov complexity. Yeah, so this joint work with Haley Goldbeck, Valentin Cabanets, and Jian Lu, they are here. So what we want to say is that now it's a probabilistic notion, but you can think of it as there's a random string that is public and it's available to all parties involved in a computation. And now my string will have small PKT complexity if given this random public string, I have a small description of it. Okay, so a little bit more formal, you can read here. So for most random strings, so these are like these public random strings, there exists a small program, and it can depend on this randomness, so it has access to the randomness. And this small program, given the randomness, deterministically produces X from this input.
Question.
Yes.
Is there some reason why the length of W and the number of steps is the same?
I'm just assuming here that the length of M is K. I'm assuming the running time is T.
No, you said the W is T of length of X steps.
Yeah.
And you also want M of W to output X within T of length of X steps.
Yeah, so I'm just using that, you know, if you run for T steps, you probably will only access T bits of randomness, and I'm giving you the T bits. That's the only reason why I maximize the number of random bits to be P of X.
Oh, I see.
Okay.
So really it's the time, and then you're saying you're going to let, you might have to think of it as if every time step you're reading a random bit. Okay.
Yes, you can think of it in this way, though you can have two-way access to the randomness too. You can think of it as being a different input tape. It's like for this notion, we want chart for the randomness complexity. That's why I give you like 2 bits of randomness if you're running in time t. So we're trying to minimize this with the length of the programs given the randomness.
The only randomness is W. There's not.
Yeah, the only randomness. Okay, so for most random strings, there's a small program that depends on the randomness and it prints X. So formally, PKT of X is we minimize over these encodings, and we take the encoding complexity such that given a random string, there's a machine with small description such that given this randomness, it prints X within Tx steps. And T is this fixed function in the definition. And just to contrast with the randomized notions we introduced before, so there we had a fixed program that was randomized that generated a string with high probability. So this is more like Chaffee's pseudo-deterministic notion. But in PKT, we switch the quantifier. So for most choice of the randomness, there's a small encoding. Yeah, I'm gonna mention that. Thanks. Okay, so yeah, that finishes the overview of this notion. So let's now compare them, try to get more intuition about this definition.
Just a quick question. So in the definition of PKT, M is deterministic.
Yeah, think of it as a deterministic machine that gets access to the randomness. Yeah.
So you give W as input to M just because M's description could be shorter than the length of W. Is that the reason why?
I don't care about the length of W. I care about the length of M.
Okay.
And
so why is a W given as an input? Because M depends.
Because M depends on W.
No, okay.
And I don't want to like hardcode W.
You don't want to hardcode W. Okay.
Is there like a Yalta kind of statement that could hold here? Like, because you have like a distribution over deterministic machines, can you somehow like?
Yeah, I'm not so sure, but I'm going to discuss the relation between this notion. Okay, so before that, just to make sure we all understand the definitions. So let's consider a setting where we have two players, Merlin and Arthur, and Merlin holds a string, and Merlin wants to communicate this string to the other player. So the second player is computationally bounded, but Merlin is not. Okay, and we want to minimize the communication complexity of sending this string or a description of the string. So now, in the first case, let's suppose the deterministic KT complexity of the string is at most k. So in this case, what Merlin can do is just pick this deterministic program of small length, of length k, and send it over the channel to the player. Okay, so that's the protocol. And now Arthur just takes a program running for t steps to recover X. So in the case X has a small deterministic complexity, we have a protocol like this. And it looks like NP, right? Like Vijay was saying. So in the case of RKT complexity, if the RKT complexity of the string is small, this looks like NMA. So what happens is we know there's a single randomized procedure that generates X with high probability. So Merlin can just submit this randomized program, and now Arthur takes the program, uses its private randomness, and recovers X with high probability. Okay, but potentially we might be transmitting fewer bits because we might have better randomized encodings than deterministic encoding. Finally, in the case of PKT, now we assume there's this shared randomness, so it's this public random string W. And what we know is that for most choices of the random string W, there's going to be some program M that given W outputs X with high probability. So now Merlin will select the program based on the public randomness and submit it to Arthur, who then uses the randomness to recover X deterministically. For most choices of this public random string, this will be a correct output. Yes, Tal?
How can M depend on, can M, I think what I'm asking, can M depend on W in some uncomputable way? Like, I don't know, if W holds on, if W is a Turing machine that holds
Yes.
on epsilon, then
Yeah,
this M.
Yeah, it's just
Otherwise, I give you another
existential definition. That is a program, although we want it to run for most steps.
Yeah, but when he chooses M, he can choose it in any way. And He looks at W and
The
chooses
time
M.
to generate M, you're saying.
Yeah.
Yeah, I don't care about the time. To
You don't
generate.
care about that.
In particular, there might be a choice of the randomness, which gives X. And then, yeah, the randomness is X. You can try to say that. More questions about the definition? Okay, so let me talk about the relation between these notions. So it's not hard to see that as you go from deterministic to randomized and then to probabilistic, which is this AM-like version, you can reduce the complexity, or at least it doesn't increase. You can also show that the unbounded Kolmogorov complexity is bounded by the PKT complexity. That requires an argument, but it's possible. And this is very similar in spirit to these inclusions of NP and MA and AM. These are the simple directions. Now, it's currently open if we can revert these inequalities and show the randomized notions coincide with the deterministic notion. But we can do it under a Hardness assumption. So I don't have much time. So let me just say that the same assumptions we can use to de-randomize MA and AM, you can also collapse these notions based on these assumptions. So to summarize, if we make strong enough circular bond assumptions, the randomized notions, they are essentially equivalent to the deterministic notions. And in particular, for every sig X, the PK complexity, the RK complexity, and the deterministic complexity are the same up to a log additive term. Yeah, I think you should also be able to do under the assumption. Okay, so that's great. If you believe in this Hardness conjecture, any progress you make with respect to the randomized Kolmogorov complexity, you can translate to the deterministic case. And this sheds light into the original questions that have been open for like several decades. Okay, but maybe these assumptions are false. That means we can still develop a theory of probabilistic Kolmogorov complexity, find applications to this theory. But its advantage is they'll give unconditional results. That's one of the main reasons we lift the randomized notions, because they'll give us unconditional results. Yeah.
Do you have any kind of lead converses here? Like, if you could get them, do you then get?
Yeah. So, for instance, yeah, Valentin was asking about RK little t. You can also prove a set of covers that if RKT and K little t are essentially equivalent, then sort of like E and BPE collapse, maybe with some small classes. One question.
This is like analog to MA. Like, is there, I guess if you define P, K poly, like a multiple round situation, is there like a round collapse lemma for P, K poly?
Yeah, that's a great question. It's not something we have considered.
Okay.
Okay, so let me move on because I don't have much time. Okay, so these are the definitions. Now I would like to highlight two applications of this new notion, PKT. And they are both in this context of average case versus worst case complexity. So briefly recap of average case complexity. So we will have a language, and we care about solving this language with respect to some distribution family. And we're going to say that this distributional problem, language and distribution are in average P if the following holds. So there's a polytime algorithm A. So this algorithm A is never incorrect. So on any input X in the support of the distribution, either it gives the correct answer or it gives a fail symbol. So it's an errorless algorithm. That's the second condition. And the first one is that for most strings sampled from the distribution, probability that it will give you the fail symbol is small. And small with respect to an input 1 to the k. So it's like an algorithmic scheme. It's an errorless algorithmic scheme for the pair L and D. And that's average P. And we can also define a randomized version called average BPP. The definition is sort of like a natural generalization. So I'm just going to skip it for now. Okay, so the first application considers the following question. So fix any problem L, and let's suppose we can't generate hard instances for L. Okay, so the assumption is that for all polytime sampleable distributions, this language L and this distribution, it's easy on average. Okay, so the problem is easy with respect to all polytime sampleable distributions. Can we say something about its worst case complexity? I can't find hard instances. Is there anything interesting I can say about its worst case complexity? So that's the first question. And in 2004, now about 15 years ago, they proved the following. They actually give a characterization. So for every language L, the language is easy in the sense over all sampleable distributions, if and only if there's a fixed algorithm such that on every input X, so this is a worst case result, the running time of this algorithm is 2 to the deterministic complexity KT of X minus the Kolmogorov complexity plus log of the size of X. So this quantity KTX minus unbounded K of X is called computational depth of the string. And they prove that this captures the worst case running time. Okay. And this T here is some fixed polynomial. So the equivalence works for every polynomial. Okay, so once I know I can't generate hard instances for a problem, this is the same as saying there's a fixed algorithm where I sort of understand the worst case time bound for all inputs. And it's connected to this computational depth. Okay, so it feels like very interesting connection, right? You have average case, and here you have worst case. Unfortunately, so the result required a very strong de-randomization assumption, which is that there are languages in E that don't have sub-exponential size circuits with sigma P2 oracle gates. So it's a reasonably strong assumption. And that motivates trying to get rid of this assumption. And what we did last year, together with Mario Zeman and Zhengjian Lu, was to show, again, once we lifted the randomized Kolmogorov complexity to this notion of PKT in particular, we can remove the assumption. So that allows us to prove an unconditional result. So we have a similar statement. The problem is easy on average with respect to all distributions, if and only if there's a single algorithm whose running time is now 2 to the PKT minus K. Okay, so we changed, we had deterministic complexity, now we have randomized, well, probabilistic Kolmogorov complexity. And this is unconditional. So any questions about the statement? Yes.
I thought the big O only contains log X and the coefficient before PKT.
Not so sure, maybe. Yeah, this statement is definitely correct. Maybe you can also get some kind of proof. I'm not sure. I think this statement is correct. More questions?
Usually work with this, but this is kind of universal search.
Yeah, I'm gonna explain the proof. The ideas of the proof. Okay, so here's the sketch of the proof. So we want to relate average case hardness with worst case complexity. And the key ingredient to connect these two statements is the existence of a sort of universal time-bounded distribution, which we call mu of T of X, which is roughly, given a string X, we assign to the probability 2 to the minus PKT of X. Okay, so this is an analogy with the unbounded case. So that's our time-bounded universal distribution. And what we prove is that easiness with respect to this single distribution is equivalent to easiness with respect to all p-sampleable distributions. That's how you get equivalence here. And then you relate the complexity with, of the single distribution, which already talks about PKT somehow, to the worst case running times, and you get PKT in the exponent. So that's the proof strategy. And I want to first tell you about how to link these two things, like p-sampleable distributions and the universal distribution. And this is done through a coding theorem. It's precisely what Eric told us about in the morning, but we're going to need a time-bounded version of the coding theorem. Okay, and so the main ingredient is going to be an optimal coding theorem for PKT. In the unbounded case, these coding theorems, they say, if you have an object, a string, and you can sample it with probability delta, then there's a representation of length log 1 over delta. And we want an efficient version of this theorem. And that's where PKT shines, because for PKT complexity, we can prove a similar statement. While for the other measures, this is still open. Okay, so here's for the formal statement. So we have a sampler, it runs in time t of n, and it generates some fixed string x with probability delta. Then we show that since x can be sampled with probability delta, we have it has PKT complexity log 1 of delta, roughly. Okay, and the running time t here is related to the running time of the sampler. So we can have now efficient encodings if we have this public random string and a statement that is essentially the same as in the unconditional version. Okay, so it's one of these key theorems of Kolmogorov complexity that we know to survive if you look at the right notion in the time-bounded setting. Okay, so that's why PKT is special for us. And yeah, we as an open problem, let me mention, we don't know how to show this optimal result for RKT or for RK superscript T. So these are interesting questions. Okay, so I want to explain to you how PKT shows up in the proof, why we need this order of quantifiers. So let's try to prove this theorem. So we have this sampler A, and it generates some X with probability delta. We want to show that this X has some sort of like succinct encoding. And the goal is to get this for PKT. Remember the definition of PKT. So for most random strings, X will have a short description given the randomness. Okay, so that's just the definition of PKT. And this is how we're going to prove it. So let's look at this sampler A. It accepts a random string of m bits, and it generates some string. And we know X is generated with probability delta. So that region is the set of seeds that lead to X. And there's a delta fraction of them. So if we could hit one of these seeds, then we could just run the sampler and recover X. So that's our goal. So let's consider a fully random hash function now that maps to m-bit strings. And let's just compute the probability that this random function is going to miss this region for all inputs, over all inputs. Okay, because this is a completely random function, it has like, it samples 2 to the k points, then the probability that it misses entirely that region is going to be at most 1 minus delta to the 2 to the k. And if we take k large enough, this is going to be a small constant. So that's just like a fully random hash function. We make sure we pick enough samples. It's going to hit that good region for us with high probability. And now I claim that for most hash functions, we're going to have a small description of X given the hash function, right? And this is just by what I said. So if you have access to this random hash function, and you know it's a good one, so you know that there's some seed that leads to X, you just store the seed, and then you can recover X, right? So that's precisely how the quantifiers they get switched here. So for most choices of the hash function, I have a seed that allows me to recover X. And this is precisely PKT complexity. So there's only one minor issue with this proof, which is that if this log 1 over delta is large, say enter the epsilon, then the number of inputs of your hash function is going to be large too. And to encode a completely random hash function will take like an exponential number of bits. While PKT complexity, if you're running time t, you want to have access to just t bits. But this can be handled. There's a way to sort of like de-randomize this construction, and that does the job. And the reason this is okay for us is because we're not really paying for the randomness. So when we actually de-randomize this, we're just reducing the encodings of the random hash functions to be at most t, but we're not paying for this t. So that's still fine. Okay, so any questions about this simple proof? Yeah, random function for you. All right, so back to this equivalence.
Why isn't like pairwise independence enough?
Sorry, if you can use pairwise independence.
Yeah, it doesn't work.
I think you might be able to do pairwise independence. The proof we gave in the paper actually is PR just against AC0, but I think that also works. More questions? Okay, so let's now get back to this equivalence. And I said the coding theorem was used to establish this equivalence between like all sampleable distributions and the special one. And the reason the coding theorem gives that first equivalence is related to the following notion from average case complexity. So we say that distribution D1 dominates distribution D2 if for every X in the support, they have the same support. Then D1 of X is at least D2 of X divided by whole n. Say X is an n-bit string. And if you now use the coding theorem, you can easily show that the universal distribution dominates any fixed p-sampleable distribution. So why is that? So let's say this is a fixed p-sampleable distribution D2. We want to show that the probability of ut of x is at least D2 x over poly. So let's say this probability is delta. Now, if we apply the coding theorem, so we know how to generate the string probability delta. So its pkt complexity is going to be log 1 over delta by the coding theorem. And by the definition of this universal distribution, you get back the original probability. You might have some overhead, but it's just a poly n overhead. Okay, so the coding theorem allows you to show that this distribution dominates any p-sampleable distribution. And the theory of average case complexity shows that when you dominate a distribution, then you can relate the easiness of a problem with respect to the two distributions. Okay, so that's the proof of the first equivalence. And for the second one, where now we focus on this single distribution, and we want to talk about worst case running time. I won't have time to tell you how to do that. Let me just make an analogy to the result for Kolmogorov complexity. So there's a result in Kolmogorov complexity that says that is the universal distribution for Kolmogorov for any problem. If the problem is easy on average with respect to this distribution, then it's also easy in the worst case. And what this proof is doing is taking that idea and make it time bounded. Because now we already have a fixed time bounded universal distribution. Okay, so there isn't much more going on here. Okay, so that makes the link between the first and the third bullet, and that establishes the theorem. Questions about this proof? Okay, so I have a second application that I would like to mention. I'm going to go a little bit faster because I only have about 10 minutes. But do stop me if that's something you want to ask. Okay, so now we would like to relate worst case and average case and to actually use this connection to get a reduction. Okay, so we want the worst case to average case reduction. And we know it's a major open problem to achieve this, to show that if NP is easy on average, then it's easy in the worst case. What was known until very recently is that if NP is easy on average, then at least you can place NP in 2 to the n time. This actually follows quite easily from the previous theorem, because there, when you assume something is easy on average, then you get this worst case complexity EKT minus K minus log. And you know that this is at most n for any string, right? So you get something is on average, then the worst case complexity is of order 2 to the n. That's a different way of kind of thinking about this statement. But you would like to do better than that. And it was open until very recently, just to show if everything in polynomial hierarchies is on average, then not NP, but like verifiers with unique solutions, you can do better than 2 to the n. So this was a biggest challenge. And Suichi, 2 years ago, showed that how to make progress, how to use meta complexity to establish, to beat the 2 to the n bound slightly, okay? Getting 2 to the n over log n. So unfortunately, his proof is a non-black box proof. That's how it managed to avoid some of the previous difficulties. But it means it doesn't generalize so easily to other models, because we can just use this easy on average algorithm as a black box. You need to do something more. So in particular, if you replace deterministic algorithms with randomized algorithms, the original proof breaks down. So we had to come up with a different idea if we wanted to show a randomized analog of this statement. And of course, there are different reasons to care about randomized complexity. One of them is in this theory of average case complexity, if you have randomness, there is a result saying you only need to focus on the uniform distribution and not over LP sampleable distribution. So this is nice. And we also want to establish connection between worst case and average case hardness with respect to randomized procedures, because these are the ones we use in cryptography, for instance. We want to make progress with respect to the connections, make sure they survive in the randomized world. Okay, so what we did was to establish this analog result for the randomized case. And let me just tell you a little bit in like a few minutes about the role of PKT in this proof. Okay. So if you think about the previous equivalence, we had the relation between average case easiness and worst case easiness. And we had this quantity in the exponent, PKT minus something. So if you want to get, instead of 2 to the n, less than that, then you want to find ways of bounding the PKT complexity of strings. Okay, so the game changes to how can I upper bound the PKT complexity of strings? And we have seen in the previous talks that there's this very powerful approach based on pseudo-randomness. Right? If I want to upper bound the complexity of a string, I can play to lose. I can use PRGs, I can break them, and I can get better encodings for the string. So we use these reconstruction procedures. This is a key idea behind Suichi's proof. You're trying to upper bound time-bounded Kolmogorov complexity of strings. You're going to use PRGs and reconstruction procedures. They are randomized. These algorithms are usually randomized. Fortunately, in the deterministic case, under the assumption that this NP is easy, Burman, Fornal, and Pavan, they show you could actually get the randomization. So under the initial assumption, everything can be de-randomized. So that's great. That's how you get around this problem of reconstruction procedures being randomized and so on. Unfortunately, if we start with the assumption, the weaker assumption that NP is easy on average with respect to probabilistic algorithms, this construction here, this proof no longer works. So we can get PRGs to de-randomize the argument. And that created the main difficulty. And in addition, if you look at how the randomness was used in this proof, so the reconstruction procedure was randomized, and it required a small amount of advice. And the advice dependent on the randomness. Okay, so you have a choice of the randomness, and then you have advice. So that's the original proof. And so we were stuck here, and how do you get around this issue, right? And so, and this is how PKT complexity was born, okay? Because you look at it, and that's precisely the notion you need to go ahead with this argument. So you want to have a notion of complexity coming from this reconstruction procedure. It's randomized, and the device depends on the randomness. So, so that's how it was introduced. And then we developed the basic theory of probabilistic Kolmogorov complexity in this paper, making sure all these steps could be implemented. Okay, so just to summarize, we introduced these probabilistic notions. I talk about the relations to the deterministic case, and I gave you 2 applications. And let me mention some directions. One is to find more applications of PKT, and I'm sure we're going to see a few of them this year. The 2 that I highlighted, they show like different aspects of the definition. Remember, one is the PRG reconstruction, where the advice depends on the randomness. It makes it very natural to use PKT. And the second application was in the context of coding theorems, because we had the random hash function and we had to fix a seed for it. So again, you have the same order of quantifiers. I'm hoping we will see more applications. A second direction is we still don't have really good bounds for primes. Ideally, we would like to show that there are prime numbers with complexity polylog n, but we are currently stuck at n to the epsilon. So more generally, we would like to show any easy and dense problem has a strings of very small complexity. So I think it's a great direction. And finally, this is more like an exploratory direction. Everything I talked about had some error, RKT, PKT. You could try to develop a zero error theory of probabilistic Kolmogorov complexity. Maybe it will have some applications. And yeah, do check the survey because it describes all these results and many more. So thank you.
Question?
Yes, just we have a special idea about whether in unified or universe, like you also going to have like how you could get a.
Yeah, that's a very good question. Let me just go back to that slide. Yes, the question is, what about deciding PKT complexity? Is it easier somehow? And is it easier to show Hardness? Yeah, I think it's a great question. Not something I try to explore.
You think like 11th version with the what's but it's little t.
Yeah, so we also need the definition of PK in the sense of Levin, which you can do. But again, it's unexplored at this moment. Even this definition itself hasn't played a role in previous results. Sweet. So thanks again, Igor. 2 hours break.